Let's review Unit 6 to get ready for the final exam. Shh, quiet please. Look up here. Okay, Unit 6 is two major ideas, gravity, Newton's law of gravity, and momentum. So let's talk about gravity. So what do you need to know about gravity? Well, if I've got one object like a planet, and I've got another object like the moon or a satellite, I'll just make it really small. Then these two objects, and we'll call this M1 and M2, Newton's law of gravity describes the attraction that these massive objects have for each other. That is, they apply forces to each other. And again, Newton didn't know why. He just said, let's suppose that they are attracted together in this way. Would this predict what we observe about the motion of the planets? And it did. It works. Newton's law of gravity is true because it works. It's not the complete description of gravity. You'll need to become a graduate student in physics to study general relativity in detail, because it's extremely mathematically difficult. But we use Newton's law of gravity because it works so well. And what it says is that if you measure the distance from the center of one object to the center of the other, and we're just going to, I'm going to call that distance r from here to here, that the force of gravity that exists between these two objects is equal to the universal gravitational constant times the mass of one object times the mass of my second object divided by the distance between their centers squared. This means that gravity gets weaker by the square of the distance. If the two objects are twice as far apart, let's say I'm right here, let's say I move object 2 and make it twice as far apart, twice as far from object 1. Does that mean that the gravity is half as strong as it was before? No. Because the gravity decreases by the square of the distance. So if you're twice as far, the gravity is only 1/4 as strong. Not 1/2, but 1/4. What if I made them 1, 2, 3 times farther apart? The strength of gravity is not 1/3 as great, but what? What's 1/3 squared? Square it! 1/9. Yes. What if I made them 10 times farther apart? It would be 1. Oh, come on. What is 10 times 10? 100. It would be 100th. You guys need this coffee more than I do. Okay, so everybody stand up and shake around or something. It decreases by the square of the distance. Okay, that's a big deal. So, now they apply forces to each other. So this is, and I'll show it as measured from the center of this. So this would be like the Earth's moon pulling on the Earth. The Earth's moon does pull on the Earth. The Earth is about 100 times more massive than the moon. So the moon's pull on the Earth makes the Earth wobble a little bit. But the Earth is dominant. The moon really circles around the Earth. The Earth wobbles a little bit because of the moon's pull. You think of that. They actually, both of them kind of circle around their center of mass, but we haven't really talked about that, so we're not going to worry about it. But here's the force of gravity, and then here's an equal and opposite force of gravity, like this. So this is the pull of M2 on M1. This is the pull of M1 on M2. Now let's take a look at this force of gravity. we said that the force of gravity is also equal to m times g. And g, if I took this little object and put it on the Earth's surface, you would know what g is, right? What is g on the Earth's surface? Yeah, 9.8 newtons per kilogram, or meters per second squared. If it's in free fall, it'll be an acceleration. But if I want to know what this force of gravity is on this guy, well, I would use m2, right? So what this allows me to do, this is the force acting, this is the force of gravity acting on this object. Well, it is the net force acting on this object. This is a free body diagram. So I multiply it by the mass of my free body, just looking at m2. And this will allow me to calculate the acceleration due to gravity at this point in space. It's also, if you consider it to be newtons per kilogram, this is the gravitational field. How strong is the gravitational field at this point? And it'll be, much less than 9.8. If you do a calculation and you get a number that's greater than 9.8, you know you've done it wrong, because what happens to gravity as we move above the Earth's surface? As we get high above the Earth, gravity becomes weaker, so g will become less. So one of the things I might ask you is, what is the acceleration of gravity at a certain altitude above the Earth's surface? If you get something greater than 9.8, you know you've done it wrong. Okay. So also one thing to remember, that this r here is, let's suppose this is like a satellite, like a spaceship or something, where the size of it is relatively insignificant compared to the Earth. This could be the Earth. What is r? Well, r is the radius of my planet plus my height above the surface. So if I give you a problem where I give you the height above the surface, you have to add the radius of the planet, Earth probably, to that altitude to get r, to get this little r from the center all the way out here. I think you can see that this is equal to the radius of the planet plus my height above the planet. So little r is equal to the radius of my planet, which I'll write as big R, plus h. What does h stand for? Height above the surface, or altitude. It could also be thought of as altitude. Is that clear? Now, what if this guy is in orbit, and we're just going to deal with circular orbits? It's moving in a circle around this big planet. Okay, like the moon around the Earth, or a spacecraft in orbit around the Earth. Well, if it's moving in a circle, what kind of force must be exerted on it? What makes things move in a circle? A centripetal force. So therefore, this force of gravity is a centripetal force. And what is a centripetal force? It's the mass of my object that's moving in a circle times the centripetal acceleration. Well, what is the centripetal acceleration? What's the equation for centripetal acceleration? V squared over r. Our speed squared over r. And centripetal acceleration, as we reviewed last time, is the acceleration that changes the direction of my velocity, not the speed. Okay, now this is only true if you're in circular orbit. Okay. Now, what this allows you to do is, if you take this and set it equal to this, it allows you to solve for your velocity. And that's called the orbital velocity equation. V orbit. The velocity of being in orbit is equal to the square root of g and then m. And now this is, What is this m? Is this the mass of my spacecraft? No, it's the mass of what my spacecraft is in orbit around. It's what's causing the gravity. So it's the mass of what you're orbiting. It's big M, mass of the Earth, probably on the final. And I will give you the mass of the Earth. I'll give you all the constants and stuff you need. Over R. So it's a simple exercise to set this equal to this. M2 cancels. One of the R's cancel. Take the square root of both sides, and you get my orbital velocity. Now also remember that your orbital velocity, remember your speed is constant, and speed is the distance traveled divided by the time it took you to travel that distance. That's what speed is, right? So if I move in a circle, say I start here and I move in a circle, what distance did I travel? I traveled the circumference of a circle. What's the equation for the circumference of a circle? 2 pi r divided by the time, right? Speed is this is the distance traveled divided by the time. Now what do we call the time it takes to make one complete orbit? Call that the period. Okay, now take a look at all this. If you understand what I've written here and can solve, basic problems with it, you are ready for the final. Also, when I said that gravity decreases by the square of the distance, and I gave you some examples, if it's twice as far apart, the gravity is 1/4 as great. 3 times as far, 1/9 is great. You might want to keep that in mind as well. I mean, you can go through all the calculations, but if you can know that, you can do some shortcuts. Okay. Any questions on gravity before we move on to momentum? All right. Momentum. The definition for momentum. What is momentum? It's a measure of how much stuff is moving. It's a measure of the quantity of motion. And we use the letter P to represent, lowercase p represents momentum. And it's got a little vector hat on it because momentum is a vector. It's by definition equal to the mass that's moving times the velocity of that mass. So this is the definition of momentum. It has units of kilograms, meters per second. Okay. Well, where did this definition come from? Well, it came from Newton's second law. Remember that we said that the net force acting on an object is equal to an object's mass times acceleration. Now in this class we're going to assume that the force is constant and everything is constant like that over time. So the force and acceleration are constant over time. So and I'm going to drop the net, just assume that F here is the net force. So the net force is equal to mass times, well, what is acceleration equal to? It's the rate at which I change my velocity. Delta V over delta T, that's acceleration. Well, then I just multiplied both sides by delta T. And I get this little equation. Here's my net force times time is equal to my mass times my change in velocity. Well, mass times velocity is momentum, so mass times a change in velocity is a change in momentum. And this little equation right here, the net force times time is equal to the change in momentum. this equation has a name. It's so important, it's such a big deal, that we've given it a name. It's called the impulse momentum theorem. When you apply a net force to an object for a period of time, we say that we have applied an impulse to the object. So the product of force times time is impulse. This is called, in physics, it's called impulse. Okay? It's different if you're talking about shopping, okay? Impulse shopping is not the same thing as force times time, okay? But physics steals vocabulary from everyday language, and it's kind of descriptive in a way. If you have an impulse on an object, that will be equal to the change in momentum. Now, not the momentum of the object, but how much I change the momentum. And again, this is the impulse momentum theorem. So a change in momentum is a product of two other quantities. And so if I have a force, if I graph the force as a function of time, I can figure out what the change in momentum of my object is going to be. Now, if the force is constant, you just say, oh, force times time equals a change in momentum. But what if the force does vary with time? Well, all you have to do, what if I had a situation like this? I had force and time. What if I had something like this? 1, 2, 3. 1, 2, 3, 4, 5, 6. That's terrible. My increments are terrible there, but oh well. So 1, 2, 3. What if I had something like this? I have a force of 3 newtons applied for 3 seconds, and then over the next 3 seconds, the force gradually becomes weaker and weaker until it's 0 at 6 seconds, and we're done. And this is the net force applied to an object. So here's the net force applied to an object as a function of time. Well, that object got accelerated, right? The object got accelerated. There was a net force on it, so its momentum changed. And this area underneath here represents how much that momentum got changed. Whoops. And so you could break it up into shapes. Okay, well, let's see. 3 times 3, that's 9 Newton seconds. And then what is this? Well, this is 3 times 3 divided in half, so that's plus 4.5. And now why do I call them Newton seconds? Because what am I doing? I'm multiplying newtons times seconds, right? So Newton second. So what do I get here? I get 13.5 Newton seconds. But what does that mean is true about how much I change the momentum? That means I changed the momentum of the object that had this force applied to it by 13.5. Now, what's a Newton? A Newton second is an impulse. Here I want to change in momentum. What are the units for momentum? Well, it's mass times velocity. Kilogram meters per second. Are these the same? Are these equivalent? Yes, they are. Because what is a Newton? A Newton is a, am I still on screen? Tell me if I'm off screen. Is a kilogram meter per second squared, right? Mass times acceleration, that's a Newton, times a second, because we multiplied by time, force times time. That cancels, the second cancels the second squared, and I get kilogram meters per second, which are the units for momentum, in this case, a change in momentum. And remember that this value here is not the momentum of the object, it's how much the momentum of the object got changed. So if you were solving a problem, you say, oh, okay, so this is going to be equal to P final minus P initial. And then you can solve for P final if you know what P initial was and all that sort of thing. And the problems I'm going to give you are going to be really, they're going to be pretty simple problems. So And I'm really going to look at the homework problems you have done and make them extremely similar to those. So study those problems. All right. So this is the first part of momentum, is the impulse momentum theorem. And this is how you use it to solve problems. The second big topic in momentum that will be on the final is our collisions and explosions. Now, when you have a collision or an explosion, you have two objects. Now, it could be more than two objects, but guess what? For what we're going to do, we're going to talk about objects colliding, just two objects colliding. If I have multiple objects colliding, it gets crazy. So, suppose I've got like billiard balls like this, like you saw in the video. Here's object 1 and object 2. Maybe object 1 is moving like this. Maybe object 2 is at rest. Doesn't have to be at rest, but this is before. So object 1 comes and it hits object 2. So this is a velocity vector here. And this says m1 and m2. Then they collide, and when they're in contact with each other for a brief period of time, maybe a hundredth of a second, they apply a force and therefore an impulse to each other, and therefore they change the momentum of each other. So they apply, but Newton said correctly, and we've observed this, we've verified this with all kinds of experiments and observations, that this is the force of object 2 on object 1. This is the force of object 1 on object 2. And what's true about those forces? They are equal and opposite. And of course, remember the famous BAM! Those forces are applied for exactly the same amount of time. Yes? Makes sense? So we can multiply that force by the time that those forces are applied. And what we see is that, here's the impulse on object 1. And here's the impulse on object 2. And those impulses are equal to each other because the forces are equal and the times are equal, but they are in opposite directions. Which means that the change in momentum of object 1 is equal but in the opposite direction as the change in momentum of object 2. And then if I rearrange this, if I add this to the other side, I get 0. So in other words, object 1 gets its momentum changed. Object 2 gets its momentum changed. But when I add those changes together, I get 0. So really what happened is this. This has a certain quantity of momentum. When it collided with object 2, it gave object 2 some of its momentum. Okay? But no momentum was created or destroyed in this collision. So it was conserved. So the way you handle, and by the way, an explosion, it's the same concept except that the objects are usually, we consider the objects at rest, but there's either a spring inside, or if it's a real explosion, you've got explosives, gunpowder or something in there. And when you ignite that gunpowder, it pushes everything outwards. But for every push you have this way, you've got an equal push the other way. And so by the same reasoning as a collision, momentum is conserved. So we start off, here's my system, right? My system. And there's no net outside force acting on my system. I'm not adding or subtracting mass from this system. So I call this an isolated system. And so if you have an isolated system, no adding or subtracting mass, no net outside force acting on your system, momentum is conserved. That's a big idea. And so the way we always start a collision or explosion problem is this. The initial momentum of my system will be equal to the final momentum of my system. Write that down when you're doing a problem. If on the final exam, I'm going to give you a collision problem. If you write this down, you've got points, even if you don't do anything else. So yay, that's easy. Now, then you look, where is all the momentum? Well, in this problem, it's all in object 1. But what if object 2 was moving? Well, here's something really simple. Take this and break it down into your two objects. It's m1 v1 initial plus m2 v2 initial. That's the total initial momentum in the system, right? That will be equal to m1 v1 final plus m2 v2 final. A lot of subscripts, but don't be scared by them. All right. Now, put little vector hats on here. This is a vector equation. Now, with the problems we're going to do, what does the vector hat mean? It means if my object is moving to the left, what do I do with my velocity? To the left means negative, to the right means positive, okay? Now, if you wrote this down and then you wrote this down, now I promise you, you can solve the problem. What would you do with this term right here if this was the problem I gave you? Well, what's true about the initial velocity of object 2 in my little example? It's 0, so this whole term goes away. But if you wrote it down and just like went, oh, okay, this is 0, you're good. But if it wasn't 0, you would just include it in there. And then, you know, obviously, I'm going to give you enough information where you can solve this equation for the unknown. The hardest thing about this problem is going to be, you know, if you set it up correctly, the hardest thing about it is going to be the algebra to solve for your unknown. For example, I could give you all the velocities and have you solve for one of the masses. Okay. I mean, that's something I could do. And it would be easy once you have it set up. So, now this raises some cosmological kind of, not cosmetological, cosmological issues. Is the universe, the whole universe, an isolated system? Is there a net outside force acting on the whole universe? Are we adding or subtracting mass from our universe? Let's just say no. Let's say yes. Yes, it is isolated, and we're not adding or subtracting mass from it. So that means that the total amount of momentum in the universe is fixed. And if for every object moving one way, there's probably an object moving somewhere else, in the opposite direction, I would bet that the total amount of momentum in the universe is 0. There's no momentum in the universe overall. Kind of weird, spooky, interesting. All right, but not on the final. Okay, so let's not worry about it. Okay, so that's it. That if you understand this and what I talked about with gravity, let's zoom all the way out. I'm zoomed all the way out. If you understand this stuff about gravity, and this tells you what to put on your equation list, right? And impulse and momentum, and collisions and explosions with momentum, you're not going to have any problem, because I'm going to give you really basic, straightforward questions and problems. Okay? Nothing tricky, because it's a final. That's it.